What's up YouTube? Today I'm back with another sensor tutorial. I will be showing you how to connect the ADXL345, as you can see in this image, to the Raspberry Pi Pico or Pico W via I2C communication using MicroPython and Thonny to start getting 3-axis accelerometer values in real time. That is acceleration in the X direction, acceleration in the Z direction, and acceleration in the Y direction. So you will, by the end of this video, have all those values ready to you and available to you in your projects. And it's very easy to set up. We're just going to start with this diagram here, where we have the ADXL345 connected to the Raspberry Pi Pico or Pico W. It doesn't matter, it'll be the same thing. And you just need 4 jumper wires. And of course, you have to have the sensor soldered. I offer the sensor soldered on my website and my Amazon store, so I'll link that in the description below. So if you are uncomfortable with soldering, or you just don't want to solder, you can buy the sensor pre-soldered. And in fact, a few weeks from now, I will enhance the soldering on this sensor, and I'll make sure it is flush on the surface and sitting flat on the surface, because I know a lot of my customers have requested that. So if you are watching this video a few weeks from now, you can go and buy the enhanced version of this soldered sensor, where it will lay flatly on a surface, which is really good for clipper applications and even other applications where you want really accurate measurements. You typically want your sensor to sit flat on a table. So that's just a quick tidbit there of where you can get the sensor and where you can buy it soldered. Other than that, it's offered many places online, and you simply need jumper wires, which are also available all over the internet. So if you're not familiar with those, go just search jumper wires on Amazon and you can find a bunch. And you simply want to connect them to a soldered Raspberry Pi Pico with these 4 connections here. So the main things you want to focus on, we have other pins you can use but that's beyond the scope of the video. We're just going to focus on powering it here. So with ground and VCC, we just want to connect to these corresponding pins. And make sure you really don't mess up these ground and VCC or mix them up, because that can actually fry your sensor. So that's something I did once on accident. I wasn't paying attention and I instantly fried my ADXL345. So just be careful when you're putting in your ground and VCC to properly power this device, or you will actually start seeing smoke coming out of it and it will stop working. And finally, to initiate the I2C communication, we just need 2 connections via SDA and SCL to pin 0 and 1 on the Raspberry Pi Pico. So it's really as simple as that to get started with I2C via the physical setup. So now that we have that set up, let's jump into the code setup. Okay, so jumping into the code for this device in MicroPython, I am using Thonny. You don't have to necessarily use Thonny, but it is probably the most popular IDE when you are coding on the Raspberry Pi Pico or Pico W. So it is just 30 lines of code, and I found a majority of this code online. Some gentleman was able to simply get the raw values from the accelerometer data, but I just converted those raw values into actual values for Gs, and 1 G is 9.8 meters per second squared. So by the end of this, you will be able to get the values in Gs for all X and Y and Z axes. So you just have these simple imports. So if you have used I2C before with the Raspberry Pi or Raspberry Pi Pico in MicroPython, you are familiar with pin and I2C, and that just initializes an I2C object, which allows us to read values from the SDA and SCL pins of this device. Next, we have the time library, and this is just the gap between the readings. You can adjust this based on your application's needs. I put 0.5 seconds just to show you how the values are looking in real time and give you a nice visual representation without them being too fast. And finally, we have the ustruct, which just simply allows us to unpack the acceleration values from the sensor, and that is the register that gives us the actual values. So here we're just initializing the I2C communication. So if you did connect the SDA and SCL pins correspondingly, as I showed you in the previous segment of this video, you should be good to go here. So just set it up exactly like this. If you are using another pin, you will have to change these values based on the pin. The Raspberry Pi Pico does have more than one SDA and SCL pin that you can use, so just keep that in mind. Next, we initialize the ADXL345. So what we're doing is we're just changing the mode. So we're enabling measurement mode by accessing the register of the power control on this device, and we're setting it a certain byte value. So this is in hexadecimal. We're not going to get into too much detail about this, but typically when you're using a lot of libraries for other accelerometers or other sensors, a lot of this is going behind the scenes, where we are setting certain values at certain registers to get the values, to manipulate the modes, and to manipulate the resolution. So I don't want to get into too much detail about this, because that is beyond the scope of this video. So what we're also doing is, another thing important here is we're actually setting the data format to full resolution, because this thing can measure data from 0 to 16 Gs at the full resolution mode. And there's other modes where you typically maybe want it to only measure between 0 and 4 Gs. And the reason you want to switch the resolution is because a higher resolution uses more power than a low resolution, and I believe a higher resolution actually has less accuracy. So it's just a trade-off in terms of if you want a higher resolution or a lower resolution. And this, we're going with the full resolution, where we can get values up to 16 Gs, the full capabilities of the sensor. And if you are interested in lowering the resolution for your application, you can look at the datasheet and see which bytes you have to set to enable a lower resolution mode. So they have a datasheet online. If anyone's curious, in the comment section, I will link it. But I would imagine that's publicly accessible, so there should be no issue in changing the resolution mode for this device. So we're just going to do 16 Gs plus minus. And then next, we are going to read the acceleration data. So we're just going to unpack it from the register where the x-axis data starts. And from there, we can unpack the x, y, and z data with this ustruct library. And finally, we just return the raw x, y, and z values. So I'm going to print those down here. So those values, I believe, are from 0 to 256, if I'm not mistaken. And those values can be converted to actual gravity values based on the sensor data sheet, which is provided online. And I found that value online, which is you just multiply those raw data values by 0.0039, and you will get a value of gravity that you can start to use, and that is a representation of meters per second squared. Okay, so we're just going to go ahead and run this code. And some other things to keep in mind is that when I first started running this code, I had this OS error, EIO, and I couldn't find the solution online. I simply unplugged and unplugged my device, and it worked. So you may run into that. So just unplug and plug the device. And if you are having more issues, let me know in the comment section down below. It could be that your device is fried or something's wrong with the device. So there are ways to deal with that. And also, if you are using a different resolution, if you set a different byte here for a different resolution mode, I think the value, the constant, you have to multiply the raw values by changes. So you have to see that in the data sheet as well. So it's not necessarily that all resolutions use the same constant to actually get real acceleration values. So keep that in mind. So now we're just going to go ahead and run this, and I will show you the raw values and the values. So my sensor is sitting flat on the table, so that means Z should be about 0, or Z should be about 1, sorry, and X and Y should be 0. So let's go ahead and run that. Okay, so Z is about 1 G, and the reason we're seeing above 1 is because this sensor should be calibrated, as many accelerometers should be. And I have videos of calibration on my YouTube channel. I'll link them right here. It's a video about calibrating the MPU650, but you can do the same thing with this sensor with the same methodology. So if you're interested in that, I'll link it right here. And if I go ahead and move my sensor around, you can see that the values simply start to change. You know, if I start vibrating the sensor, we can see that we're getting values. If I vibrate fast, let's see if we can get it to 3. Okay, see? I can only vibrate it so fast, but you know, if you are having really high impact applications, you can see resolutions up to 16 Gs. So that pretty much sums it for this video. So we connected this device to the Raspberry Pi Pico, and we are getting values for acceleration, real acceleration values, not just raw acceleration values that we can use in our project. So if you enjoyed something, or if you learned something in this video, please like, comment, subscribe to the channel. It would mean a lot. Also, if you have any questions or suggestions, let me know in the comment section down below. And you know what I say, guys, stay tuned, and thanks for watching.